I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew Falkowski, and I'm joined, as always, by my co-host, Taylor Sparks. And today we have a very special episode, one that we've been wanting to do for a long time, but haven't really found the best way to approach it. But through our collaboration with GE, we have two experts on superalloys, and we just got out of a fantastic interview with them, and we're really excited for you all to hear it.
Yeah, I think superalloys are one of these really challenging topics, and it's easy to talk about them sort of really lightly, but it's hard to get into the details. But I think it's worth it because there's not a lot of great resources out there on this topic, and I think that we've done it justice here.
So without further ado, we'll hop over to our interview with them. All right, we are joined by Sanjay Sundhi and Jeff Williams from GE Research. Do you guys want to introduce yourselves?
All right. So, hi, good morning, Taylor and Andrew, and all your viewers. This is Sanjay Sundhi, a metallurgist by training at the Materials and Manufacturing Team in the research wing of GE Aerospace. And much of the work that we do is high temperature materials. And I guess the centerpiece of that is nickel superalloys. So look forward to today's discussion.
Okay, and good day. This is Jeff Williams. So I'm based at the GE Aerospace Engineering campus in Cincinnati, Ohio. I'm currently the chief engineer for metallic materials for the aircraft engines portion of our business. So really excited to be with you to talk superalloys.
Well, welcome to the show, both of you. We're delighted to have experts in superalloys on the show. And maybe to kick things off, can you give us a bird's eye view of why superalloys matter in general and specifically to General Electric?
Sure. That's a great place for us to start. So General Electric has been involved with superalloys both as a user in terms of products as well as a technology developer within our internal research and engineering arms, really since the get-go, going back to the early part of the 20th century, where the United States and some of the allies at the time were looking at the possibilities for adapting turbo superchargers into jet engines. So we had the opportunity to be part of a U.S. Army program. Lots of really interesting stories behind that. There's a book written about them. It was a secret program at the time, of course, and it looked to adapt technology around gas turbines that had been developed in the UK and bring that technology to a application with aircraft. And so one of the key principles behind the technology is the Brayton cycle, really elegant thermodynamic cycle. And one of the things that makes it successful is thermal efficiency. And the more optimized you can create that machine and that cycle to increase the pressure ratios and increase the temperature and the energy extraction from the fuel that is introduced into the system, the more efficient it is. And so that's where we got started, and that set the stage for the need for very high temperature metals. And we had the opportunity to participate and be a part of many decades of superalloy development, and it's still one of the very core technologies that enables our products that we're making today.
That's awesome. You mentioned something that doesn't get brought up as much. Everyone talks about, higher efficiencies is higher temperatures, but it's also the pressure differential, right? So does that put interesting implications on the material development because of the mechanical properties that have to withstand those pressure differentials?
So I'd say yes. I mean, they're very much linked. But as we think about the buildup of pressure in a compressor, the stresses that are put on the casings, so essentially pressure vessels, and we have, of course, very stringent engineering requirements on how those are expected to perform, and the level of safety required in the design. Certainly, to make sure we get a good balance of both lightweight structures and the capability to withstand those higher operating pressures. Yeah, it's certainly a piece of our design.
Okay.
And you had mentioned a little bit about pushing temperature, but what are some of the challenges of employing materials at higher and higher temperatures? Surely things start to break down a little bit and properties aren't as good as they are when measured at room temperature.
Certainly. So one of the key things that we need to do anytime we're contemplating a new design or going through a new product design cycle is look at the kind of the full range of conditions that that component may see, and consider a variety of different damage mechanisms that may be operative in that region. So we do a lot of characterization, looking at mechanical properties, environmental properties, and then I'll add another piece in here that's really important to superalloys in particular, and that's the stability of properties over time. So as we're running at these very high temperature conditions, what's happening microstructurally within the material that could be changing the properties during the life cycle. So we need to make sure that we account for any of those types of effects. And then on the environmental side, we of course are looking for, in an uncoated material, looking for a real stable protective oxide scale to form.
Yeah.
But then of course that's interacting with the underlying metal and changing the composition locally. So coatings then come into the picture and allow us another whole set of engineering tools that we can use to help monitor that. But again, it creates a material system that we're trying to understand and make sure is performing in the way we expect it to be.
Yeah, so from a material system standpoint, everything you described makes this a really challenging thing to sort of optimize for, because there's so many competing properties and constraints you have to work with. So with that sort of in mind, Sanjay, can I ask, why is it that we settled on superalloys? What is it that makes them so uniquely suited for this application?
So great question there, right? Um, Most materials find it very difficult to even maintain their strength with temperature. And superalloys are unique in a way, and that's probably what we will get into, is that not only are they able to maintain their strength can actually go up with increasing temperature, say all the way up to 1000 Kelvin or in excess of 750 Celsius. So that's something truly unique about them, that instead of losing strength with temperature, they can actually increase their strength with temperature. You can get as high as over 1000 megapascals of yield strength at temperatures of over 1000 Kelvin. And then even when the strength starts to decrease after that temperature, they can maintain excellent strength and capability all the way up to 1100 Celsius. So you can start to use them, and we use them up to 90% of their melting point in turbine blades, right? So no other material really offers that kind of a capability, and hence the term superalloys.
And what typically constitutes a superalloy, in terms of its elemental composition?
Hmm. So when the whole superalloys field started out, the base element was one amongst iron, nickel, or cobalt. Now, if you think of the periodic table, all of these three are actually neighbors in the periodic table, right? So they are immediate neighbors. They have very similar atomic number and weights, but they all have different crystal structures at ambient temperature and pressure, right? That's something people don't notice. But the superalloys in general would have either iron, nickel, or cobalt as the base element, in which then other additional constituents would be added for a range of properties. So, for example, oxidation resistance and corrosion, right? Substantial amount of chromium would be there for that. And when the superalloy development started, that chromium would be in the range of 15 to 20%. But as the temperature started to get pushed to higher and higher ranges, chromium oxide will eventually volatilize at high temperatures. So chromium content basically then became lower and aluminum content became higher, right? So you start out with nickel, iron, cobalt, one of those, you add chromium, and then you have to add key strengthening precipitate forming elements. And those are typically aluminum, almost exclusively it will be there, titanium, tantalum, and niobium. And these started out as sprinkles, but increase more and more in terms of their, shall we say, contributions or constituents in the superalloy. And then refractory elements to reduce diffusivity, because you're looking at high temperature, and also to form carbides at the same time. So elements like molybdenum, tungsten, rhenium. So these are what we would call the major elements that would be there. And then there may be special purpose trace elements or magic dusts, if you will, like boron, carbon, zirconium, and hafnium, that have very special purposes that we would get into later. So that's sort of the makeup of the compositional or chemistry brew, if you will.
So Sanjay, that's fascinating. I once heard a talking about alloys for aviation, and wasn't talking about super alloys, but it's talking about the skin that they use in all these planes, and it was this I think it was aluminum copper mixture. I can't remember what it was, but then they talked about how it was slowly refined over time. It was decades in the making. How it was slightly changed, all the way to today, where that specific alloy has, I think it has 10 different alloying elements, and they are precise in their ratios of those in that composition to like the thousandth place. So
Right.
that's just incredibly specific. So I'm curious, like, did super alloys, as you're describing the makeup of these things, did it follow a similar sort of incremental, slow improvement over time, or how did we get to the alloy? First off, what is the alloy we're using today? What's the name of it, and how did we get there in terms of timeline?
So I think superalloys, when we talk about anything as a big breakthrough, right? We forget sometimes that there were some incremental things that happened before that in the background, which truly made them possible, right? So Jeff was talking about early 20th century, and two major things that happened in early 20th century were, for example, austenitic stainless steels and nichrome. And those two were supremely important in terms of laying the foundation of development of superalloys from there on. For example, austenitic stainless steel told metallurgists that you need to be in the face-centered cubic or the closed-packed regime of the iron and steel domain for it to be viable for high temperature, right? So one, rather than doing BCC phase, which is a lower temperature, one went to the face-centered cubic phase. Nichrome in parallel, which is again 1910s, showed that you have to add chromium to nickel to be able to get good high temperature properties. And part of that was due to oxidation resistance, but people did not realize at that point of time is that chromium additions, for example, lower the stacking fault energy of nickel substantially, which increases its high temperature creep performance. So the groundwork was that how do you get fundamental high temperature strength using face-centered cubic materials, and nickel came out on top amongst others. That was one part. And then Jeff talked about essentially the drive for superchargers and jet engines, and the First World War played a role in that, right? So everyone across the globe in the Western Hemisphere started adding different elements to these concoctions. So people started to add aluminum, titanium, tantalum, niobium to the basic brew of nickel chrome, or in case of Monel, say nickel copper. And that is when people started to discover that the strength suddenly went up, and strength actually started increasing with temperature. Now, no one knew at that time why it was happening, because what actually was giving this high temperature strength, gamma prime precipitate, were so small, and there were no electron microscopes available at that point of time, so one could not see them, nor did one know the mechanism of how it was happening. So that empirical part of the development in some ways happened through a lot of serendipity, if you will. And that's how superalloys came into being. And once people realized adding aluminum, titanium, etc. helped, it was essentially then a matter of creating more and more brews across different labs in the world, and then trying them out. The understanding really followed much later. Earlier, it was just a matter of making something, testing it, and if it worked well, put it out.
Yeah, that makes sense.
Hey, while we're on the subject of elements, do you mind if I add a little bit of a personal anecdote like Sanjay was
Please.
describing here?
Yeah.
So I'll say some of my early interests in superalloys came about in retrospect, probably because as I was starting my material science undergraduate education, for reasons I still probably couldn't explain well, I decided to take an elective course in the chemistry department that was an advanced inorganic materials chemistry topic. It wasn't required for the engineering program, but for some reason I thought I should take this. And amongst the things we were required to do was to memorize the entire periodic table. So I spent some time that semester making sure I knew how it was organized and why it was organized the way it was, and then ultimately be able to fill in a blank one on a final exam. But then as I began to get into metallurgy and some of the advanced undergraduate courses, I was fascinated particularly by superalloys because, hey, it covered a lot of space. It seemed like there were a lot of options. I didn't understand the reasons, like Sanjay just described. I'll say a lot of the reasons why certain elements were selected. But it was appealing that we had such a big palette of alloying possibilities. And so as a person entering my education in the field, that was something I found both fascinating and challenging at the same time. And then as I've started to work in the industry, it was really interesting that TMS, which has a great heritage in promoting and supporting industry and academic and other collaborations in superalloys. They for many years have hosted these conferences and workshops, and their icon for that, the famous Seven Spring Superalloy series, is a periodic table image that has all of the elements that have some role in the superalloy space on the cover. And so when I had the chance to go to my very first one of these conferences, I believe it was back in 2004, they gave away some beer glasses that had the Superalloys logo, awesome. And so I proudly took a couple of those home and still have them here in the cabinet. And I'll say they've been a lot of fun as my children were going through middle school science and eventually high school chemistry to occasionally pull that out and quiz them a little bit with the periodic table. But like Sanjay said, it's a unique field in that we do have so many varieties, and it's resulted in many alloys that find application in engines. So if I think you'd asked earlier about what alloy do we use today, the answer is we use many. We of course try not to have too many low usage ones, but depending on the type of part in the engine, they use different classes of superalloys, and that's really part of the benefit as well, that we have this broad spectrum of capability, and we can sort of focus based on what works well in a rotating disc, for example, versus a blade that sits on that disc versus a casing, like those pressure vessels we were talking about earlier. So that's just a little story about the periodic table and superalloys and kind of how they go hand in hand when we're talking about the subject.
Fantastic.
Yeah, that's a really great point. I think my dad actually had a similar story of a class he took where the final exam was just a blank periodic table. I think that was in grad school though. But yeah, no, it is really fascinating that you have such a large number of possibilities, and that those possibilities aren't just a simple mixture, that they actually manifest in terms of a really unique and special structure as well. Sanjay, you had alluded to these precipitates. Maybe you want to talk a little bit more about them and maybe dive into the microstructure of superalloys and why it's so special.
Absolutely. So a common denominator right across all the different superalloys, and in this case, now we are talking about nickel superalloys, because iron and cobalt based superalloys sort of fell by the wayside for different reasons till there is a more recent interest in cobalt based superalloys. But nickel based superalloys, there's a common denominator, and that is gamma prime phase, and this is an ordered face centered cubic phase. So now just imagine a face-centered cubic lattice structure, And this unit cell, assume all the nickel atoms, for example, occupying all the face centers, and aluminum atoms occupying all of the corner atoms. That is what brings out the stoichiometry of Ni3Al. And gamma prime phase essentially has a stoichiometry or a chemical formula, if you will, of Ni3Al. And elements like cobalt, etc., can go and replace part of the nickel, and elements like titanium, etc., can go and replace part of the aluminum. But essentially, you have this ordered face-centered cubic phase, which is now sitting in a matrix of a regular face-centered cubic matrix. Now, so if you look at the image which is associated with this podcast, what you will see is neatly arranged squares, which are essentially cubes in 3 dimensions, where you have these bright phases. These are the gamma prime phases. These are the precipitate embedded in a continuous matrix, which is gamma, which is essentially a nickel cobalt chrome solid solution, right? So the difference between the two is essentially that the matrix does not have any additional particular order or arrangement of atoms within. It is a simple face-centered cubic arrangement, whereas within the precipitate, the atoms have a very specific site that they belong to, and there is chemical ordering. And this chemical ordering is really the genesis of much of the special properties that superalloys derive, and that superalloys eventually exhibit.
And maybe we want to get into a few of those properties, because there's quite a few that these precipitates grant the materials.
Right. So if we think about let's say regular particle strengthened materials or precipitate strengthened materials, right? So let's start with particle strengthened materials, where you could have things like aluminum oxide in aluminum. You're essentially talking about very small fractions of incoherent, hard, generally covalently bonded particles, which are now finely dispersed, and their sole job is to be an obstruction to dislocations which are carriers of the plastic strain or plastic deformation, right? So that is how they become effective. If you go to things like regular precipitate strengthened materials, like say aluminum lithium alloys, now you start to get coherent precipitates which are not necessarily shall we say very hard. They have their own ductility, but they prevent dislocation motion by virtue of being ordered. And dislocations, if they were to get into the precipitate, they would disturb the order within the precipitate, right? So there is a huge energy penalty to a dislocation getting into the particles. So that is how they provide strength, that they do not allow the free flow of dislocations through the microstructure or the lattice. What happens in nickel superalloys is essentially it is precipitate strengthened materials on steroids, because as you alluded to that microstructure, that how much of volume fraction of precipitates exist, that you're talking about up to 70% of, shall we say, gamma prime in blade alloys, and anywhere from 20 to 60, 65% of gamma prime in disc alloys. You just have a very, very large volume of these. And the way they strengthen is very different from conventional understandings people may have about, say, two-phase material and composite structure. If you took gamma prime phase in isolation, say Ni3Al, its elastic constants or modulus or strength are actually not very different from the nickel matrix that it is embedded in at all. So it has a very similar yield strength, it has a very similar elastic modulus, shear modulus, bulk modulus. So it is not a classical composite strengthening at all. The way it is providing this strengthening, first of all, is via the chemical barrier, that if the carrier of strain, that is dislocation, were to enter the particle, it will be creating a different order or arrangement of atoms, which the material doesn't like, and there has a huge energy penalty to that. So it stops dislocations from getting in. So that is one key attribute of nickel superalloys. Now, that by itself does not explain why there is going to be an increase in strength with temperature, and that is an altogether different mechanism, that not only do you get high strength as it is even at lower temperature, but now what happens is in nickel based superalloys in particular, that as the dislocations enter the gamma prime precipitate, they split into what are called superpartials. So this is actually getting quite technical over here. Intermetallic phases like Ni3Al, by virtue of being ordered, the dislocation Burgers vectors are quite large, which means the energy associated with the dislocations is huge. So to reduce the energy, these dislocations split into partial dislocations, and these partial dislocations are bounding a fault called APB or antiphase boundary, and now they are moving through the lattice. The challenge is that this APB or antiphase boundary, it has a very high energy in nickel-based superalloys, right? And this high energy of the order of say 2, 3, 400 millijoules per meter square um, allows now the leading dislocations to sort of find some easier pathways, and those easier pathways can be moving out of its natural comfort of the 111 plane to a 100 plane, and which is not natural for dislocations to do under typical under normal circumstances in face centered cubic materials, right? So when that happens, it cross clips momentarily or for a short distance, but realizes that it has lost its way and cross clips back onto another 111 plane. So now you have these two pairs, these two dislocations bounding a fault within, spread across multiple planes, parallel 111 planes, and this sort of becomes what in mechanics terminology we would now call a dislocation lock, and it is sessile, it cannot move. So what you have done is essentially created an obstacle in the path of any incoming deformation or dislocations, and all of them now get stuck at this obstacle. So you need to keep on raising the stress to overcome these obstacles, and strength keeps on increasing. Now, what does temperature have to do with it? All of these cross-slip events, these are thermally activated. So thermal fluctuations
Oh,
can allow this cross-slip to happen. If there were no thermal fluctuations, this cross-slip will not happen. The dislocations will remain planar only on the 111 plane, and you will not form any locks. So with increasing temperature, you form more and more of these, and you are creating more and more strengthening obstacles within the gamma prime, and hence increasing the strength with temperature.
that is, I actually had not understood that before. I appreciate that explanation because it seems so counterintuitive. Most alloys, I mean, just common sense is you heat them up, they don't get harder and stronger. And yet when you frame it as the defect that's causing the strengthening is essentially a thermally activated, defect,
Right,
that makes sense. The higher the temperature, the more of them there are, the more strengthening you get. That is really interesting.
right.
I have a question. So we have now an idea of the understanding of the structure and the microstructure that gives rise to these properties, and yet you can't ever in material science separate the composition of the material from the processing to make it. And oftentimes the processing is also related to the components, right? And so
Mhm.
some components have to be made a certain way, whether it's net shaping or whatever else. So do you run into conflict? Maybe conflict's the wrong word. Do you run into trade-offs that you have to have when you're looking at which components and the ways that you can actually process them?
Oh yeah, absolutely. Jeff, you want to take that question?
Sure, I can comment on that. So that raises a really great point about superalloys and the components that we make from them. So we do employ a variety of process routes to the final component. Almost all start with some type of a vacuum melting process, and certainly vacuum melting technology, as it was coming up around the same time as superalloy compositions, I'll say was a big enabler to getting superalloys introduced into industrial applications. So from there, how you can of course create your initial melt, create an ingot, and then you have a variety of possibilities for how you take that. So one route is you take that initial vacuum induction melted ingot and you further melt it. You do some refining. So you do perhaps some additional steps like electroslag remelting or vacuum arc remelting, and result in a very refined, clean ingot. This is a great approach for generating input material where you can manage segregation. So not too much alloy content that you get a lot of segregation during these melting stages, and also very clean. So you have a very controlled inherent anomaly content to give the design engineers and ultimately the product itself a well predicted suite of properties. So no anomalies that could cause anything unexpected to occur. So you take that final ingot, then you break that down, you convert it through various mill processes to a billet or to bar, and then subsequently do some near net shape forming, usually a high temperature forging operation to get to a near net shape, and then some further thermal operations like heat treatment to set that microstructure in the most optimized manner, and then machine to a part. So that's, I'll say, one of our most common routes towards making critical rotating parts in jet engines, as well as a variety of the airfoils, so the high temperature compressor airfoils. There's other routes. When we want to go to higher alloying content, we can take that same vacuum induction melted ingot, which may, in the case of higher alloying product, have some inherent segregation to it. But to work around that, we can then atomize that ingot into powder. And then we have a very homogeneous composition in the resultant powder. Then we can use powder metallurgy techniques to either convert that powder into a billet and do some subsequent forging operations for, again, a very clean, refined, and now higher alloy content material with mechanical property advantages. Or more recently, we've seen taking powder such as that and using it in some type of an additive manufacturing technology, whether a powder bed, a laser powder bed or an electron beam powder bed operation, or a variety of larger format additive techniques where we've borrowed from the welding industry techniques for imparting energy to that powder and using it to build up near net shapes. And then the final one, I'll say, in terms of process paths that's quite common in our industry, is casting. And so that's a good tried and true approach towards making a lot of different metallic material systems. But again, you take that starting ingot and melt it, pour it into some type of a mold. And again, process technologies have evolved really alongside of superalloys, such that we can do a variety of approaches to making an equiax casting. And then I'll say a key technology that came about along with superalloys, and really for superalloys in a lot of ways, is directional solidification and single crystal casting. And so our very highest temperature superalloys, which we use in the hot gas path of turbine engines, can be made from a single crystal. And then we eliminate the effects of grain boundaries on high temperature properties such as creep, and can actually make some very, very interesting shapes that our technology experts in component design and component cooling can take advantage of casting techniques such that they can create cooling passages and really interesting architectures to not just optimize the material performance, but also the overall system performance and how you deliver cooling air to these very high temperature parts, and then also maintain the optimal aerodynamic efficiency of the airfoil shape itself. So really a bunch of routes. We have them at our disposal, and superalloys composition and their resultant properties really allows us to take advantage of a number of these techniques to get to the parts we have in the engine.
And I imagine you're using different processing techniques for different components, especially based on the temperature, as you alluded to. But why, I guess, if you're designing maybe a new component, why would you choose one processing route over another?
Oh, that's a great question. So let's start with, we'll look at three categories of components. I'll say that are our most common turbine engine components that are made from superalloys. So the first is a rotating disc. So this is a very high energy structure. It's in the engine. It's rotating at very high speeds. And again, these superalloys generally aren't real low density materials. That's something we can talk about a little later. So it has the challenge of supporting its own weight as it's rotating at speed, as well as the weight of the blades that it's carrying. Um, and so it's both a real high stress component, as well as it's a concern that if there were to be any type of flaw develop or cracking, if that part separates and ruptures in the engine, it releases a very massive amount of energy, and so not a good situation in terms of product safety. So, we spend a lot of time and effort making sure that our designs have damage tolerance, that they have well understood properties, and that the superalloys we make them from are very, very clean. And so that's really what drives us towards either this, multi-melt steps with what we call cast and wrought processing. So we do a triple melt, followed by billet conversion, followed by forging, and then a variety of inspection techniques get applied following all those operations. And it gives us a structure that's polycrystalline, so we can use grain boundary strengthening in addition to the precipitate strengthening that Sanjay was talking about, and the solid solution strengthening that comes along with the alloy, and really understand in detail, even in location specific within that rotor, what its mechanical properties would be, and have high confidence in the integrity and quality of that material. So that's, I'll say, a common approach for these high energy rotors. Either use cast and wrought metallurgy, multi melt steps followed by conversion and forge, or the powder metallurgy route, where you make the powder, again, very clean gas atomized powder that gets subsequently converted, usually through a compaction and extrusion process to billet, very clean billet that then gets forged into shape. And again, that's a pathway that we can really take advantage of some composition techniques and understanding heat treatment to get the right grain structure and grain size that gives us a very damage tolerant material, such that not only do we design to avoid any type of crack initiation, if there were an unexpected crack initiation, we still have residual life in the form of crack propagation in these so-called damage tolerant materials. And our company really pioneered that with a material system called Rene 88DT back in the late 1980s, which really changed the game for us in terms of design, and having a material system and a process route that gave us both very good properties in the general sense, tensile, creep, low cycle fatigue, as well as damage tolerance in the form of crack growth, fatigue crack growth resistance. So that's really how we pick our process path for high energy rotating parts. Then for the other two categories, I'll say we have some more dials, because there they're lower energy parts. If there were to be an issue in the design or the material system, the consequences of failure are different. They're still undesirable, but they fall more in the category of durability for the system. So for the flow path components, so these high temperature airfoils, this is where single crystal castings offer us a way to make complex geometries that both optimize the aerodynamic shape of the airfoil, as well as the cooling passages. So these are filled with, traditionally we use what was called serpentine cooling. Many of us in the industry have moved to, I'll say, more advanced internal geometries for cooling blades. And being able to accomplish that in a casting itself, and then do subsequent finishing and coating operations on those parts, it really results in a good product. And we've used that to increase our product durability. And so those parts are usually managed by the amount of time and cycles that have been on the engine. And you actually can go in with think of a borescope, like a little camera, or that goes in on a device into the engine when it's on the ground for an inspection, and we watch the deterioration of those, and we see, okay, well, they're looking a little more worn out, and then we manage those on condition. When they get too worn out, we take them out and put in new ones. That of course is, it's a cost for the airline, the operator, and so we look to give them the best life possible and still meet all of these thermal efficiency desires that we have for the overall engine. But by using castings and superalloys and coatings, that's allowed us to really improve the time on wing, alongside of increasing the thermal efficiency of the product. And that's always a huge tug, because it's like, well, if you make the part hotter, it will have deterioration, in the form of thermal fatigue or oxidation sooner. And so trying to both progress our turbine efficiency and our fuel burn in the product, as well as maintaining our customers' expectations around how long will it last before it needs a replacement, has been one of the huge challenges for materials engineers and mechanical and aerothermal engineers within the industry. And then the final one is these static structures. So these come in a huge variety of shapes and sizes, and things like cases and seals, heat exchangers in some cases. And here's where you try to optimize your geometry and your material properties. So it could be a casting, could be a ring rolled forging if it's an axisymmetric kind of part. It could be, a fabricated part where you take a bunch of different pieces together, sometimes from different alloys. We've got a few really interesting sealing structures, static seals in our engines that we use multiple superalloys in the same final component, but we use joining techniques such as electron beam welding or brazing to create this component that uses a mix of materials. Sometimes we want a higher coefficient of thermal expansion to maintain clearances in some areas, to have them be tight in one area and more open in another. And so it's really a great opportunity for materials engineers and our component designers to pick, which alloy suits best for this location. And sometimes one location in a part has a different desire from a design standpoint than another. And we have these options that have developed over time, and we continue as both of industry and a company to find new opportunities to make those kind of parts. So it's a great place to be if you're a metallic materials type engineer, because it's every new product has some type of challenge. We're building on history, but we're always looking for new innovative ways to improve the product.
So that's a perfect jumping off point for my next question was, there's been decades of work into improving these. And you just talked about the incredible thought that goes into how they're manufactured to get the right microstructure for the right application. And yet we're always asking more, right? We're asking more of these engines and more of these tools. I'm participating on a new funding agency call where it's the Ultimate program, where they're looking at new ways of even envisioning what superalloys can do going forward. And part of that is saying, do we need to stick with nickel superalloys, or do we need to look at entirely new base alloys altogether that are more refractory? And some groups are looking at, high entropy alloys as candidates, and others like ours are looking at other base materials such as niobium that might work a little better. I'm curious, what are your perspectives on sort of design approaches for the next generation of what these alloys will be?
So I'll say I think we're at a bit of an inflection point with the superalloy development, and I'm glad you brought up the external program work that you're involved with, looking at other classes of materials that bear some similarities to superalloys in terms of they're designed for extreme temperature, and also I think those new types of systems can learn a lot from the history of superalloy development over the decades. But I'll say for the superalloys we've been working, we still have, I'll say, some opportunities to make a variety of improvements that are meaningful, not just to the company where Sanjay and I work, but I think to the industry as a whole. I'll say that the guiding principles in our company right now, GE Aerospace, we have a moniker SQDC, and that stands for safety, quality, delivery, and cost. And if I think about superalloys, the ones that we use today in quantity, some of which have been in our product portfolios for decades. You're thinking of like alloy 718. I mean, that's been in GE products since the 1960s. But we still are making product with that today, and we want to make sure that we're delivering the product that results in the best safety, quality, timely delivery, and then optimizing costs for our products. So as we think about our priorities in superalloys, we come back to that a lot as a guiding principle. And then in addition to those, we of course are looking at enabling the future of flight. So we've talked a lot in this discussion about thermal efficiency and continuing to eke out a few more degrees of capability of alloys. And this has been a kind of our our bread and butter thinking about alloy development for a while. That's how we end up with kind of materials like if we think of ATI's alloy 718 plus. It was intended to be similar to alloy 718 but better. It had a higher temperature capability, but maintaining all of the things we like about 718 in terms of its formability, weldability, and so forth. So that's just an example. And I'll say internally we've had a variety of alloy studies where we take an alloy we currently like and we add plus 50 or plus 150 degrees Fahrenheit. And so that still persists, but there's a number of other opportunities we have to make sure that the current products are being made in a way that's consistently clean, that matches the supply chain capabilities, because the supply chain network that our industry works with is global. And so some have different generations of equipment in terms of furnaces and presses for forgings, and so making sure that we're continuing to push that forward, and then bringing alongside new developments in inspection technology. There's been huge advances in recent years in ultrasonic inspections, and linking that up with digital tools such as automatic defect recognition and improved processing of the scans. That's teaching us new things about these very legacy materials, which we can use and incorporate to help those SQDC objectives that I was talking about before. But I do want to circle back to the question about other alloy systems. Like I said, we're at a bit of an inflection. We've learned some new things in recent decades about cobalt-based alloys. Turns out you can get L12 precipitate strengthening in those. So we've been following that type of work. We've also seen a huge amount of innovation come alongside of the additive machines. So this is something that the GE has been very involved with. We've actually entered the business of making both electron beam melting powder bed machines as well as laser powder bed melting machines. And so we've started out exploring those with some superalloys that we're familiar with, but there's a lot of interest in how does that process technique open the door to other alloy systems that we've either explored in the past and they didn't really fit into the current the process routes and designs of the day versus where we're at the present. So that's a real intriguing opportunity. And there's a huge amount of literature that's out there right now, and a lot of work on optimizing nickel and cobalt superalloy materials for those types of process routes and the kind of component flexibility that additive design permits. But I think the real interesting thing will be is these refractory materials you're talking about that really garnered intense interest from a variety of potential end users. And those materials, like Sanjay was mentioning before, we move from kind of body-centered cubic alloy systems to these face-centered cubic alloy systems, and then got the coherent precipitates, and we've enjoyed a lot of benefit from that. A lot of those refractory systems, we're now back to those things wanting to be body-centered cubic. And is there a pathway towards getting something akin to these, L12 ordered gamma prime strengtheners like we have in the FCC systems and superalloys? Could you alloy those systems in such a way to develop something comparable? It's obviously different because we're going to be still in this BCC base. But had the opportunity to talk with some people in academia who are studying that pretty intensely. And I was impressed to see the work and the tools, the digital tools that they're bringing to the table. And I couldn't help but notice that a lot of those were derived from, the work that we've done over the decades in superalloys, and using that as an initial use case for, computational materials engineering. And so I think they can learn a lot of lessons from the history of superalloys. And I think there's also room to go the other direction. I mean, I'll say in our business, density is pretty important. And a lot of those refractory systems, they're inherently higher density types of materials. And also we are very dependent on kind of long-term durability and oxidation. And those refractory systems are known to have huge challenges. And I know there's people out there working
this
coding.
Is far from solved.
Oh, yeah. Yeah. And so I just think we're entering this really interesting point where I'll say for nickel-based superalloys on their own, we'd say, well, we're at a bit of inflection point. But given all that's going around us in the materials industry and some adjacent industries to aircraft engines, I think the aerospace community at large, is keenly interested in bringing together experts from both superalloys and the historic refractory alloy experts to see how we can learn from each other and work together. So I'm really excited. I'm glad to hear that your institution is part of some of those studies and research that's going on.
Yeah, so it's a pretty complicated space, as you've mentioned. There's quite a lot of variables to juggle. So what sort of tools is GE using to explore some of these new superalloy compositions internally?
I think that's a great one for Sanjay to take a stab at. He's been, in fact, Sanjay and I first started working together when Sanjay was building a team some years ago for materials modeling at GE Research, and certainly has been at the forefront of this. So go ahead, Sanjay.
Absolutely. So we talked about all of the underlying fundamentals, which makes basically superalloys tick, right? And one of the things that you would have noticed, and I think we all called it out, that the things that make superalloys really super are actually quite counterintuitive, and those phenomena do not occur in a lot of or most other materials. So one problem that happens is that the learnings that you may have, for example, from steel or aluminum alloys or titanium alloys, you cannot bring the same learnings to nickel superalloys because the whole underlying physics is very different, which means that the kind of quantities that you need to go out and optimize fundamentally are very different from the ones you may be looking at in other material systems. And so the key approaches that we are looking at are essentially physics driven models itself, right? So if you want to design a high strength, high temperature capable superalloy, the broader recipe, if one were to articulate, it is going to be, well, have a lot of gamma prime, right? That is one. B, have the gamma prime itself to be very strong. C, have the gamma prime to be very stable, because as Jeff mentioned in the beginning, that all of these materials are going to be operating at very high temperatures. So the microstructural stability itself is quite important, that they should not be coarsening as exposure goes along, and they should not undergo different other phase transformations, right? Now, to achieve all of that, what you then require is ability to predict phase stability and phase diagram within the nickel superalloy periodic table space. That is one. Also predict that what size of precipitates you are going to form for typical processing conditions, which is determined by both the interfacial energy and diffusivity and the phase diagram. The challenge is that many of these quantities that you need to predict, which are going to drive these phenomena, for example, interfacial energy between gamma and gamma prime, right? They are so low in terms of their number. For example, they can be as low as 10 or 15 millijoules per meter square, that they are essentially noise in any calculations that you are going to be able to make, even atomistic calculations. And then to be able to predict these numbers at high temperatures is an even bigger challenge, right? So what we do is essentially, there is a huge amount of learnings and knowledge that we have in-house, which one would call, say, company memory, right? We use our understanding along with all of this data and couple it with physics-based models to predict what phases would form, what would be the length scale of those phases when we manufacture them, what would be the stability of this microstructure as it is in service, what will be the initial strength, and what would be the evolution of strength as one goes along. So we essentially use these modeling approaches at different length scales as well as for different phenomena, and then couple them together to balance the competing, shall we say, objectives to design the superalloys. So these involve CalFET type approaches to get phase diagrams, to predict when the gamma prime is going to be appearing and disappearing, that is solvers. what sort of segregation may appear during solidification. Jeff talked about that quite a bit. And then our ability to homogenize, and that is something we can again leverage models that we have developed, that which alloys would be easier to homogenize, and for a alloy which we believe will have wonderful properties, what would be the best time temperature cycles to homogenize that, what would be the precipitation, shall we say, morphology and length scale that's going to come about, what will be the strength that it is going to be giving us, right? So that's one large approach. And then couple that with machine learning, bring in all the data that we have developed over many decades of in-house work, couple that with high throughput experiments. For example, when JC Zhao was at GE, he pioneered the diffusion multiple work, right? He went over to Ohio State and then to University of Maryland. But diffusion multiple is a great example of high throughput screening, where you can create a wide range of compositions very quickly and see what phases are going to appear. So that gives you information about what you're going to get in terms of composition and phases. And then characterization gives you, methods give you mechanistic understanding. So we are essentially coupling advanced characterization, high throughput experiments, physics-based models, and data-driven approaches for the next generation of alloy design.
And with how counterintuitive a lot of these properties are and how maybe unusual they are, do you have to end up writing a lot of internal or custom codes and programs in order to actually model some of these materials?
So I think the key is to understand what to compute exactly. And once you understand what to compute, then you can resort to some of the traditional approaches. So for example, we talked about how the order within gamma prime, atomic arrangement within gamma prime poses a huge challenge for dislocations to get in, right? And that challenge is in the form of antiphase boundary energy. So you have to understand that now you have to compute antiphase boundary energy, and that has to be for, let's say, the octahedral or the 111 plane. So that input comes from physics, that what needs computing, but the way to compute it, then one can resort to atomistic simulations to be able to compute that. And then one says, okay, the counterintuitive part is that just knowing the antiphase boundary energy for 111 plane is not enough, because that tells me how strong it is, but it doesn't tell me anything about propensity for cross slip. Because propensity for cross slip is going to be determined by how much is the difference of APB energy between 111 plane and the 100 plane. So then I go out and compute the APB energy as a function of composition and temperature for 100 plane. So what questions to ask, that comes from the understanding of the counterintuitive physics. But how to compute those numbers is something where we use internal expertise as well as a large body of work in academia, where different research groups have developed methods to compute these numbers fundamentally.
Maybe a question for you, Jeff, is related to what we think superalloys can and can't do going forward. Do you think that there are some realistic bounds that we have to put on what we can expect for next generation superalloys?
As far as realistic bounds, that's a really good question. We've thought about that a lot within our team of experts that works these materials. There are certainly challenges with being able to meet the balance of properties as we go further. So when we add certain elements, those elements may be expensive. They may be hard to procure or create pressures within the supply chain to obtain them. So those are some I'll say boundaries and things that we look at very, very closely. I think Sanjay mentioned early on, we were focused this talk on nickel superalloys, but one of the big reasons that kind of cobalt superalloys fell out of favor was there were a couple of different crises in the 1950s and again in the 1970s where it was really hard to get your hands on cobalt. And so out of necessity, that shifted people to looking at nickel. And we're here today, and there's some renaissance in cobalt materials that's really interesting. But things like that um, have some impact, as well as you make materials stronger and harder, and I'll say more desirable from an end application perspective. That sometimes makes them harder to process, just harder to make them. And as we're making materials, we need to make sure that we can respect worker safety in all of the operations that go into melting, conversion, and so forth, as well as making sure that if we define a alloy composition with a really narrow heat treat window, can even control a furnace to the level of fidelity that the material requires to get that really well optimized microstructure. So those are the types of things that are making us look in different directions, maybe looking at different disciplines and experts around industry and academia to help us talk through, are there potential solutions that aren't obvious or weren't part of our kind of historical thinking about superalloys. So I think there's some stuff happening there that will allow for some new breakthroughs to happen. But ultimately, I think the heart of your question is there are some fundamental physical and thermodynamic limits that do constrain us. And I'll say the good news as an industry, not to detract from our good discussion here on superalloys, but these new classes of materials, things like ceramic matrix composites, have opened new possibilities, new classes of refractory alloys, like we touched on earlier. And these things are always being compared and contrasted with each other, and that's really one of the beauties of material science.
So maybe another question, as you're trying to push and find the best possible alloy, how do you balance sustainability with that? And what are maybe some of the other considerations for adding new elements to superalloys? And maybe just to tack that on, because it's related, how do supply chains need to change in order to meet the demands of some of these new alloys?
Well, I think one of the things I was just going to mention was that if you look at cobalt, right, Jeff mentioned, so there are multiple competing pulls for cobalt. So with electric vehicles, there is another huge market for that requires cobalt, right? So if we are competing with that, we are going to then struggle in terms of availability of cobalt for superalloys. So I think there are going to be these geographical, geopolitical challenges as well as the competing markets themselves. Yeah, Jeff?
Yeah, I was going to say the same. We do have a focus on strategic sourcing of a variety of metallic materials and elements that go into metallic materials and coatings. And really that cross-industry look is becoming more and more important. Where is another industry emerging where there's going to put some pressure on the types of materials and base elements that go into ours? There's geopolitical issues. There's a variety of concerns that come to play. So it's fascinating. And it's something that I've been a part of quite a bit in the past couple of years as the world's been changing and new industries are taking shape and things are happening geopolitically that make it challenging to get into some areas where we have historically. So I'll say it's a great mix of engineering, kind of the strategic purchasing and sourcing functions within our business, the government relations arm of our business. These are a great opportunity for these disciplines and experts to work together to help be at the front of it, so that we're not caught off guard and reacting to something. But like you said, we're going to try to help shape our industry in a way that minimizes our exposure to those types of risks, so that we can keep the delivery, as it's been committed.
Well, we've had a fantastic conversation today. I think a lot of the topics that I was thinking about, in sort of summary, we sort of touched on. Maybe one final question from me anyways would be, I'm curious from your perspective, looking at the broader field of all the scientists and industry participants, what they're working on, is there a blind spot that we as a community are not looking at enough?
So that's a tough one. Sanjay, you got something there?
Absolutely, and that's something we continuously keep asking ourselves, right? So, so one of the so I won't necessarily talk about it in terms of blind spot. A lot of the alloy composition development has happened by broader, shall we say, guidelines. Okay, but there may be some very special regions in these chemistry spaces. This is a 10-dimensional chemistry space, and there may be spaces in between which no one has, for example, found so far. And the only way to get to that is really not going to be running design of experiments experimentally, because then you're talking about one in a gazillion chance, literally. So I think the blind spot in some ways is, and that's something which, with the help of academia and with the help of wider community, I think we are getting over, is quantifying as much as possible of the knowledge, because in the end it's a very, very small differences in quantities, or very minutely measurable quantities, which make all the difference to the properties of these superalloys. And I think if we can a predict all of them to great degree of accuracy in this 10 element space, and couple them all together, then we may start identifying spaces in this big universe, if you will, of periodic table, some compositions or some brews which are going to be truly special. And even NASA, when it puts out its Vision 2040 document, it's telling that it is that far out. So I don't think one it currently has the wherewithal to predict all of that to the level of accuracy it is needed. The recognition is there, but a lot more needs to happen to actually convert it to reality.
And Sanjay's answer there inspired a couple of other thoughts, and maybe you guys would want to splice this back in a little bit earlier.
Okay.
But thinking about potential blind spots within the superalloy field, particularly with the forward look, I can't help but think about the history of how we got here, and how even though this technology has been undergoing development, both revolutionary and evolutionary, for decades, uh, it's been a pretty focused, tight knit community of people working on it, really from the get go. And we've seen several generations of those engineers and scientists come through. But I think that we're unique in the fact that you could probably play one of these, 6 degrees of so and so kind of games, and quickly, find a connection with a colleague in the industry. So that's unique from when we're thinking about blind spots. Because we know each other pretty well, and we tend to talk amongst ourselves and meet at various committees and conferences. But we also want to bring in new people, new students, new researchers, new people into industry that can help challenge us and bring some experience, in different branches of the material sciences, and maybe even in some other adjacent fields. But anytime I think of superalloys, I can't help but remember just points of connection back to those early days. And if you'll indulge me, just a short story.
Yeah.
When I was on the first week or so of my job at GE in the late 90s, I started in a materials development group, really a superalloy development group, and was brand new to the industry, straight out of my undergraduate education. And was being introduced to certain projects, and the engineer that was mentoring me and helping get me started mentioned that, hey, there's a guy who sits down the hall one afternoon a week. His name is Earl Ross, and Earl was the inventor of many of the alloys that we use today. And you should set up some time to go meet him and talk to him, because he's really an important historical figure. And he was long retired, but he still came in one afternoon a week to,
Of course,
to think and ask questions. And so I said, oh, that sounds great. And so I asked my mentor, I said, well, what should I ask him? What types of questions should I go in and be prepared to talk about? My mentor says, nothing. You just go in there and listen. He's going to talk. He's going to he's going to tell stories. You take whatever notes you can and try to remember as much as possible. So sure enough, I scheduled time with Earl Ross and had this one-on-one session with him where he went through decades of superalloy development, war stories, battle scars, huge successes. And it was fascinating. I was ready to go after taking that, few hours that afternoon. And just to have the chance to have met someone who was active during that in the 1950s, 60s, 70s, when things were changing really rapidly, and then later got to touch projects with a number of, I'll say, the next generation of Superalloy developers, and they've recently retired. So people like Dan Krieger, who invented Rene 88. We had a great tag team, a trio of engineers at GE Aerospace in the late 90s and through the 2000s. Ken Bain, Dave Maurer, John Groh, Eric Huron, who did a lot of work on that next generation of rotor materials. So I had a chance to meet with these guys and really work alongside of them and learn from them over the years. So I just can't help but give a couple of shout outs to people who were there, and they maintain this connectivity to the very, very early days of the superalloy industry. And they give us so much to build on. But looking forward, we need to bring in new talent, new capabilities. It's been incredible, the amount of academic interest in superalloys that really started around the year 2000. Brought in a number of different university groups around the world. And they started talking and working together. And I think that was a game changer for a lot of the modeling techniques, the characterization methods that were becoming in vogue during that time. But there's more to come. I think there's really a huge opportunity for this next generation of engineers to pick up on this heritage, but then also continue this continuous improvement journey for existing alloys and open up new solutions.
And I think add to what Jeff just mentioned, right? Many a times when we are thinking about, Jeff talked about earlier that X alloy plus 50F or X alloy plus 100 Celsius capability, many a times that effort of developing that gets tied down to where one started from. And I think that becomes sort of a blind spot that we land up with many local optimizations, and which gives us that alloy plus maybe 100C or 50C, but it may not always give us necessarily a global optimal solution. So to Jeff's point about to be able to bring in new talent, right, new students, new thinkers, any further developmental program should be tied to the objectives of what we are developing, and not necessarily tied to existing chemistries. So it should only be tied to learnings from existing experiences and not to the existing compositions at all, because there may be opportunities in very different compositional spaces in that multidimensional superalloy space, which haven't been explored yet. And that can only be done if one focuses on objectives and is open to trying out the whole space, potentially in a computational way, and then evolve the topmost candidates experimentally.
Well, yeah, thanks again for coming on and sharing your knowledge. Like I said, I think this is going to be a great episode. And I'm a little bit jealous. You're talking about all these different alloys and elements that you can include. I work as a material scientist in the nuclear industry, and so we basically take only 10% of the periodic table, and even then, some of those aren't even allowed to be included in there just because of neutron economy and such. So that's really cool and special that you get to work on that.
Okay, well, we will be in touch then. Thank you all so much.
All right, well, thanks, guys.
Behind every GE innovation is a breakthrough material. First, it was the tungsten filament that enabled GE to bring light bulbs to the mainstream in the early 1900s. Later, Lexan polycarbonate, invented by GE scientist Daniel Fox, ushered in generations of new plastics, from compact discs and DVDs to the helmet visors of astronauts who walked the moon. Through the latter decades of the 20th century to now, advances in nickel-based superalloys, titanium aluminide, the introduction of ceramic matrix composites, and the first 3D printed metal jet engine parts have helped propel commercial air travel beyond the Wright brothers' first 12-second flight at Kitty Hawk to some 100,000 flights happening around the world every day. Materials innovation has always been at the core of what GE does and central to the progress our products have driven. My name is Joe Vinciquerra. and I'm proud to lead the Materials and Mechanical Systems Technology Organization at GE Research. Together, we are an interdisciplinary team of aerospace, mechanical, materials, chemical, and manufacturing engineers and scientists working to advance the state of the art for complex mechanical systems, innovative system-level designs, advanced materials, and revolutionary manufacturing methods. Every day, our researchers explore the boundaries of cutting-edge technologies that are poised to change the world. Whether shaping the future of flight or aiding in the transition to a zero-carbon energy future, our team helps GE stay at the forefront of innovation, enhancing our products and delivering for our customers. If you're ready to see, move, and create the future, consider joining our team at GE Research. To view our latest job openings, you can visit us at www.gecareers.com to learn more. That link is also available in today's show notes, and thank you for listening to today's episode.
The Materialism Podcast is sponsored by Materials Today. You can visit materialstoday.com to stay up to date on the latest happenings in the materials science field and read some of their fantastic articles that they've published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
Thank you for listening to this episode of the Materialism Podcast. If you've got any questions or feedback, send us an email. Reach out to us. We're easy to get a hold of. You can find us at materialism.podcast@gmail.com, or we're actually much more engaged on Instagram and Twitter. So our Instagram handle is @materialism.podcast, and you can connect with us there. We also post lots of fun pictures and additional stuff about the show, some behind-the-scenes things. So check us out there. It would really, really help us if you would leave us a 5-star review on iTunes, Spotify, Google Play, wherever you listen to your podcast. Leave us a positive review, and it will help us expose the show to new people. That would be really great. Finally, we want to give a big shout out to Alphabot and Kolobyte. They're the ones who make the really cool music that we use in this podcast. So thanks to them. We think they make good stuff, and we think that you should support them. You can find their stuff on Spotify and YouTube. So with that, we will see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.